Good morning, 8th and 9th grade. This is Tuesday morning, and I am going to do your science class. So move out of the way so you can see. 8th and 9th science study guide answers. This will be my last science presentation or my last science video. You will do the test after you check this, and if you do not have the study guide done, please don't watch this video. You push pause and go back and do your study guide. And some of you have been calling me with questions. That's great. I would love to hear from more of you. If you get in trouble, get stumped, can't find the answer, call me. Don't watch this video to get the answers. You call me to get the answers. But once you got your lesson completed, then you do this and check your study guide and use that to study for your test. We'll talk about that as we go through a little bit your test here. So here we go. We're talking about stars, and the very first one, I may not read all these questions. I might just tell you the answer. The very first one has 1, 2, 3, 4, 5, 6, 7 answers, and I will not read those. You can turn back in the book and get the answer. I hope that's where you looked. For the ones you didn't know, you can get your own definition for those terms. I will start with number 2. In number 2, says this away. It says, from the inside to the outside, name the 4 regions of the sun. Okay, you start inside, it's core. And then the next one is going to be the radioactive zone, the convection zone, and the photosphere. Core, radioactive, convection, photosphere. That's your 4. And number 3, it says this way. How does the sun get its power? In which region of the sun does this process occur? Okay, the sun gets its power from nuclear fusion. Okay, nuclear fusion, and occurs in the core. And number 4 asks, which part of the sun do we see? That's the photosphere. Obviously, we can't see the core. Photosphere is the outside layer. Number 5 asks, if 251 CF nucleus is bombarded with neutron, it breaks into a so-and-so nucleus and a CD nucleus and 7 neutrons. Is this nuclear fission or nuclear fusion? And that answer is nuclear fission. Number 5 is nuclear fission. Okay, when you have it a breaking down like that, you have a fission. Okay. Let me keep going. Number 7. For both the nuclear fusion that occurs in the sun and the nuclear fission that occurs in a nuclear power plant, what can we say about the mass of the starting materials compared to the mass of what's made in the end? Okay, regardless if it happens in a power plant or if it's happening on the sun, what can we say about what we start out with, and then whenever it explodes, what we have left over? And that answer is number 7. In both processes, mass is converted into energy. Okay? Thus, the starting material is larger than the ending materials. So, it is significantly more what we start out, and when we explode and pick up all the pieces, we just got a little bit left. So the difference is there's less. Number 8 says, why is it important for a nuclear power plant to have a nuclear explosion? Why is it important for a nuclear power plant to have a nuclear explosion? It's important for a nuclear power plant to experience a nuclear explosion because a power plant does not have significantly more than the critical mass of the large nucleus that is breaking apart. Oh yeah, it is impossible for a nuclear power plant to experience a nuclear explosion. Yes, is it? And you say yes, it's impossible because they do not have a large mass of product or of mass, a large quantity of mass that can explode. They just have a small amount. So you just have a little boom, boom, little explosions because they don't have a big pow like the sun does. And number 9 says, why is nuclear fusion considered a better option for energy production than nuclear fission? Okay, why would you want nuclear fusion versus nuclear fission? And nuclear fusion is a better means of producing energy because there are no radioactive byproducts. There is no chance of a meltdown, and starting materials are very cheap. A nuclear fusion is a better option. No, let's go that route, right? Let's do nuclear fusion rather than fission. Fission is explosive, and then you have the radioactive, the byproduct that's dangerous, and yeah, let's do that. Okay, well, let's read the next question. If nuclear fusion is a better option, why don't we use it? Oh, why don't we use it? We don't. Why don't we? Oh, we cannot use nuclear fusion. The answer, we cannot use nuclear fusion yet because we cannot master the technology to make it economically feasible. It takes more energy to get it to explode than what the energy comes from the explosion. Huh. Well, we'll have to help scientists figure that out. Or, I guess maybe we'll have to allow God to help us and to help scientists figure it out. Because it happens on the sun, so it can't happen. God will know how to do it. We, scientists, and me, don't know how. Okay. Number 11 says, now we're going to switch from the sun, we're going to switch to stars. And I'm going to tell you right off the bat, you have that chart, yes, on your book, you have that chart of the main stars, and then you have the supergiants and the superclusters, and yeah, you need to know that for a test. And you have it right here, so study the idea of how that chart is made. Number 12 says, which of the stars in number 11 is most like our sun? Wait a minute, is that what I was supposed to tell you? No, that's number 12. Did I give you 11? Oh yes, I'm sorry. I back up here. I didn't get you 11. Using the HR diagram below, classify the following stars. So, number A, a magnitude 1, spectacle letter K. Spectacle letter K. Number 1, you should have had for A, you should have had a red giant. And then for B, you should have had main sequence. It's in the main sequence of stars. Number C, you should have had supergiant. And number D, you should have had white dwarf. So let me repeat. Red giant, the first one, main sequence, supergiant, white dwarf, A, B, C, D. Now, number 12 says, which of the stars in number 11 is most like our sun? Well, that's so, if you remember, our sun is in the main sequence. So that would be B, main sequence. Number 13, it says, order the 4 stars in number 11 in terms of increasing size. Okay, put them in order from size. You should have put it this away for 13. D first, B, A, C. Okay? And number 14, it says, order the 4 stars in number 11 in terms of increasing brightness. Okay, and then you're going to use your absolute magnitude chart. And you're going to go D, B, A, C. Exactly the same as 13. D, B, A, C is 13 and 14. Now, number 15. Which of the stars in number 11 is the coldest? A. A is the coldest. And if you look, he's the closest over to the red zone. He's not over by the blue. He's the coldest over by the red. Number 16. What similarities exist between the novas, supernovas, and pulsating variables? Okay, what's similar in all those stars? All 3 of these stars have their brightness changes radically with time. Okay, their brightness get bright and dim, bright and dim. All three of these kinds of stars. That's what they're similar. Now number 17 says, what's the difference between novas, supernovas, and pulsating variables? Okay, what's different? They all get bright and dim, bright and dim, bright and dim. The difference is, the big difference is their lifetime. Pulsating stars last a long time. Supernovas exist very briefly, and novas are somewhere in between. Okay, supernovas just go boom, and they're done. And then the novas go boom, 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 boom. And the pulsating variables, they just keep going. Boom, 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 boom. They never stop. There you got it. That's their difference. Number 18. What most likely formed the Crab Nebula? The Crab Nebula was most likely formed by a supernova. Supernova is your answer for 18. Number 19. What are the two methods of measuring the distance of stars from the Earth? And which of the two is most accurate? And which can be used to measure long distance? Okay, the two methods are Parallax method and the apparent magnitude method. Okay, the parallax and the apparent magnitude method. The parallax method is the most exact. Parallax is the most exact. Because remember how we looked at it from this angle, this, and then when we spin halfway around the Earth, we looked at it from that angle, and we can measure like a triangle, parallax. Now, which is the one, the apparent magnitude method is used to measure long distance. When you're way out there, the apparent magnitude method works. It's not as exact, though. Number 20, it says, why are Cephet variables so important for measuring long distance in the universe? And it got a long answer, but I'll condense it down. It means it's because of their brightness and the distance go together. So I'll read their answer. Cephet variables are important for measuring long distances because they seem to have a relationship between their period of flashing and magnitude. That allows them to be used in the apparent magnitude method for measuring long distances in the universe. Okay, so their period of flashing and their brightness helps scientists guess how far away they are. Number 21. What are the four basic types of galaxies, and which type does the Milky Way belong? Okay, four types. Some of you are calling me, asking me the question. You said there's only three types. No, if you turn to the next page, there's only three on the picture. And you have the spiral, the lenticular, the elliptical, and the fourth one is irregular. It's a combination of all those. And the Milky Way is spiral. And matter of fact is, you know, in the Milky Way, we're in the spiral, and it's got little spirals out the side. And our solar system is actually on the way outside edge. It's on one of those little spirals. The main part of the Milky Way, we're not even in that. We're on one of those little spirals out there, or our sun is in our solar system. We're about to fly off. All right, and now let's go to number 22. It says, fill in the blanks. Okay, I'll fill in the blank. Star groups together to form galaxies, that's the first one. Which group together to form groups, that's the second one. And which groups together to form clusters, that's the third one. Which some of these groups together to form superclusters. Number 4 is superclusters. So you got galaxies, groups, clusters, superclusters. And number 23 says, for the first three answers you gave in number 22, give the names that apply to those in which the Earth's solar system belongs. Okay, so tell me which galaxy we belong in. Milky Way. Yeah, thank you. Milky Way. Which group do we belong in? Local group. I say they name that because it's close, right? Someone that's local, they're close. So we belong in the local group, and that group belongs in the Virgo cluster. The Virgo cluster. Number 24. Why do most astronomers believe the universe is expanding? Why do scientists believe that it's getting bigger and bigger and bigger? It is because, they got a big long answer, but it's because of the red tint. Okay, most astronomers believe that the universe is expanding because the light from nearly every galaxy experiences a red shift before it reaches the Earth. The red shift increases the farther the galaxy is from the Earth. Okay, there's a red shift in the way you can see the planets, or no, the galaxies. And they say that's because they're moving away from each other. Remember the two methods that they move away? Oh, that's number 25. If the universe is expanding, does the geometry of the expansion matter? If so, why? And yes, that answer is yes, the geometry matters. Because, if so, why? Okay, the geometry of the universe expansion makes a big deal of the difference. Do you believe that the Earth is the center and everything is expanding out from the Earth? Or do you believe that the Earth is just part of the big galaxy situation out there and it's just a part of another planet out there and it's just moving apart like everybody else? So the difference is like you got the Earth here and everybody else is moving away from the Earth. All the other expanding away from the Earth. Or you can have the Earth out here with everybody else and everybody just expanding like we did on the balloon. When we blew up the balloon with the little dots, as the bigger you got the balloon, the farther the dots came apart. It didn't make a bit of difference. It didn't have a center. That's the difference. The theories that, yes, I shall read that. The theories that can be developed for the formation of the universe depend on the initial assumption. So, the theory, it makes a difference on what do you believe. Do you believe the Earth is the center, or do you believe that there is no center? There is no place, that they're just all expanding away from each other. I'll let you decide that. That is all for today. That's the end of the question. And then you'll have to read my favorite astronomy joke. He tells you that one. And I will let you get ready for test. Are you ready? Anybody got questions? Give me a call. Here we go. I'm going to pass out the tests, and you can do them today. You can do them tomorrow. You should have actually got them this weekend. So go for it. And farewell to science class. It's done. See you next year.